Welcome to day 4 of differential equations. Last class, we looked at a specific way of solving a first order differential equation, be it homogeneous or inhomogeneous. We saw that we could use integrating factor to solve the differential equation. That is, we could find an expression we could multiply every term in the differential equation by, which simplified the left-hand side to be just a product rule. Today, we are going to take another trip down memory lane. Remember in Calc 3 how we spent some time discussing conservative vector fields and non-conservative vector fields. And if you remember, there was a specific type or a specific test to determine if a vector field was conservative. We had a couple different ways to determine it, but the one we're concerned about today was that if if the curl of f is equal to 0, then the double integral over your region is also going to be equal to 0. And an alternate expression for this was the line integral along C of m and n, where m and n are the components of the vector field f. So that told us that f was conservative. And this had to be true for every path for it to be conservative, but the easy test was if the curl of f is just always equal to 0, then we have a conservative vector field. But a consequence of being a conservative vector field was that there existed an f such that the gradient of f was equal to our vector field f. It may feel like I've forgotten that this is a differential equations class. I assure you I have not. For example, we consider y dx plus x dy. This equals 0. We have a potential function f of xy is equal to xy. Because the gradient of this function is the derivative with respect to x is y, the derivative with respect to y is x, and we get back this equation up here. Okay, remember that. That's something we want loaded into our L1 cache right now. So now that we've loaded conservative vector fields and what it means to be a conservative vector field into our memory, let's look at a differential equation. A differential equation in this case, we're going to be looking specifically at a differential expression. We're dropping off the equal sign. A differential expression m of xy dx plus n of xy dy is said to be exact differential if there exists an f such that the gradient of f is equal to mn. And that differential, m dx plus n dy, set equal to 0, is an exact differential equation. Now, I wanted to preload this other stuff about differential equations into about multivariable calculus into our heads, because this should seem very familiar, right? We're saying there's a potential function. We're saying we have an exact differential equation if we have a potential function. Remember, we also had a way of testing that, right? And that was if the curl of the vector field that we were in is equal to 0. And that came straight from the fact that we observe anytime we started with a function of x and y, I took the derivative with respect to x, the derivative with respect to y, and then I took the second partials. The second mixed partials was always equal. That is to say, the derivative of m in this case with respect to y was equal to the derivative of n with respect to x. Or equivalently, we might have written this as dn dx minus dm dy is equal to 0. Other than the existence of the word differential in today's notes, it seems unclear how this is connected to differential equations. Well, we're building the connecting tissue. One can imagine asking, well, is just an expression that I give you, is x squared y cubed dx plus x cubed y squared dy, is that equal to 0 an exact equation? Well, this is a Calc 3 question at its heart. It's saying, if I construct f equals x squared y cubed, x cubed y squared, is this a conservative vector field? And we generally would apply the curl test to this. The curl of f, which is the derivative with respect to x of x cubed y squared minus the derivative with respect to y of x squared y cubed. Derivative with respect to x is 3x squared y squared. The derivative with respect to y is 3x squared y squared. And we get that that does indeed equal 0 for all x and y. So yes, this is an exact equation. Let's now come full circle, pardon the pun, and use this information to solve a differential equation. Let's solve this differential equation subject to the constraint that y of 0 is equal to 3. Based on what we've talked about so far, it's not really clear where to go from here. The only thing that we've really demonstrated right now is an ability to determine if this is a conservative vector field. So let's determine if this is a conservative vector field. Let's calculate the curl of f here. The derivative with respect to x of x squared minus 1 is 2x. The derivative with respect to y of 2xy is 2x. And we get that this is indeed equal to 0 for all x. So conservative. But how does that help us? Well, we know a conservative vector field has a potential function. So I've shown that this is conservative. That means we can find a potential function f of xy whose gradient is equal to 2xy x squared minus 1. So let's find that potential function. I know that the derivative with respect to x of our function is equal to 2xy. Invoking our memory of Calc 3, multivariable calculus. So that means that f of xy has to be equal to the antiderivative of this with respect to x is x squared y plus some constant with respect to x. So it could be any function of y. We also know that if I take the derivative with respect to y, I get x squared minus 1. So the derivative with respect to y of our function, which is x squared y plus some function of y alone, has to be equal to x squared minus 1. The derivative with respect to y of the left-hand side is x squared plus some function of y, and that has to be equal to x squared minus 1, which means that our function of y is negative. The derivative of our function of y is -1. So remember, we are solving the differential equation 2xy dx plus x squared minus 1 dy equals 0, subject to the constraint that y of 0 is equal to 3. And so far, what we know is that f of xy is equal to x squared y plus some function of y. And the derivative of y is -1. That's what we know so far. Well, if the derivative with respect to y is -1, then that means that this function, which is constant with respect to x, and the derivative with respect to y is -1, is at most -y plus some constant of integration. So we can refine our f of xy, which now we know looks like x squared y minus y plus some constant of integration. So our differential equation is solved by this potential function f of xy equals x squared y minus y plus some constant of integration. We do have the issue that here we have two independent variables, and this is ordinary differential equations, which means we have one independent variable and one dependent variable. So we must be looking at a level curve of this. So let's say we have this equal to 0. We could choose any level curve we wanted to. It's just going to be offset by our c. So you might say, I'm going to choose the level curve f of xy equals 1. Well, go through it and see what you get. This is what we're looking for, though. We need y of 0 to be equal to 3. So we need, when we plug in 0, to get 3 back. So we have 0 is equal to 0 squared times 3 minus 3 plus our constant. So our constant in this case is equal to 3. If you chose a different level curve here, your constant would be different. But when you rewrite this, 0 equals x squared y minus y plus 3. Solve it for y. We have x squared minus 1 times y. Is equal to -3. And so y is equal to -3 over x squared minus 1. We solved the differential equation without doing anything new, really. The only spot we had to sort of invoke any new rationale was going from here to here, saying, oh, I can't have two independent variables in ordinary differential equations. We need y to be a function of x alone. So I'm going to choose a level curve of this. That's the only spot where we had to sort of think outside the box or do something different from what we did in multivariable calculus. We also note perhaps that this only works if our differential equation is exact. So we check to see if it's exact. And if it is, then we can find a potential function and solve it for y to get y as a function of x. But not, if we remember from multivariable calculus, the majority of the vector fields we come up against aren't conservative. And so that means that the majority of the differential equations we're going to come up against aren't exact. But it'd be a lot cooler if they were. So let's say we have the differential equation xy dx plus the quantity 2x squared plus 3y squared minus 20 dy. If I want to determine if this is exact so that I could use my understanding from multivariable calculus, I can calculate the curl of a vector field associated with this. The curl of f here would be the derivative with respect to x of this, so 4x. The derivative with respect to y of this, which is just x, and I get 3x, which is not always equal to 0. It's only equal to 0 when x itself is equal to 0. And that's not great. That's not exact, which means we're not guaranteed the existence of a potential function, which means we can't use our pre-existing understanding. But we have two formulas we can try. We can try an integrating factor to make this exact. If I can find an integrating factor to make this exact, then I could solve this using integral calculus. The trick is just finding that integrating factor. Our integrating factor that we know so far only works for first order linear differential equations. And this is decidedly not linear. So in a separate video, I'm going to post the rationale for this equation if you care about it. For our purposes, it's entirely possible you don't care about where this came from and you just care about being able to use it. That's a legitimate life choice. I'm not here to judge. If I multiply everything in this differential equation by y cubed, I get xy to the fourth dx plus 2x squared y cubed plus 3y to the fifth minus 20y cubed dy equals 0. And the curl of this new vector field, we'll call it F1, is the derivative with respect to x of this, which is 4xy cubed. The derivative with respect to y of this is 4xy cubed, and that does indeed equal 0 for all x and y. And so now I can find a potential function here. So we can find now a potential function f whose derivative with respect to x is x squared y to the fourth, and whose derivative with respect to y is 2x squared y cubed plus 3y to the fifth minus 20y cubed. That is, we know the derivative with respect to x of our potential function is xy to the fourth, which means that f of xy is 1/2 y to the fourth x squared plus some function of y. And then the derivative with respect to y of 1/2 x squared y to the fourth plus some function of y is equal to 2x squared y cubed plus 3y to the fifth minus 20y cubed. So phi prime of y is 3y to the fifth minus 20y cubed, which means phi of y is 1/2 y to the sixth minus 5y to the fourth plus our constant of integration. And we get that our function f of xy is equal to 1/2 x squared y to the fourth plus 1/2 y to the sixth minus 5y to the fourth plus our constant, and we need to choose a level curve of this, arbitrarily choosing 0 to be that level curve. So the solution to our differential equation is 1/2 y to the fourth plus 1/2 y to the sixth minus 5y to the fourth plus c equals 0. And you can check for yourself. You can see if, when you take the derivative with respect to x and the derivative with respect to y, if you indeed get back to this original differential equation. When you do, you actually get this differential equation, but note that you can factor out a y cubed out of all of this, provided that y itself is not 0, then you do indeed get back to this differential equation. So the question right now is, well, how did I come up with this y cubed? How did I get that integrating factor? Well, given m dx plus n dy equals 0, that is not exact, but we want to make it exact. We're going to try two different things. We're going to try m sub y minus n sub x divided by n. And we're going to try nx minus my over m. Now, each of these is its own differential equation, but the idea is if one of these differential equations is easy to solve, then we can find an integrating factor mu. And again, there's a lot of assumptions that went into these. We don't need to know those assumptions per se. I will be posting another video, or I'll be talking about this in class about where these came from. But it is entirely possible that all we care about at this point is, well, how do I do it? And these equations are what we're trying. In the previous example that we just did, where we had m was xy and n was 2x squared plus 3y squared minus 20, right? This was the previous example we just did. We might have tried one where du mu dx is equal to the derivative of x with, or the derivative of m with respect to y minus the derivative of n with respect to x divided by n. And when I look at this, I say, I don't really want to deal with that because that is not particularly nicer than what I started with. But when I try the other one, in x, the derivative of n with respect to x minus the derivative of m with respect to y over m. Now this becomes a bit nicer because of stuff canceling out. We get d mu dy is equal to 4x minus x is 3x. 3x divided by xy, provided that x itself is not 0, is just 3 over y. And what we have here is a separable differential equation. This is 1 over mu d mu dy, and that's equal to 3 over y. If I integrate both sides with respect to y, I get the natural log of mu is equal to 3 natural log of y plus a constant of integration, which conveniently we're just going to leave off since we're just looking for an integrating factor. And so we get mu here is equal to y cubed. That is exactly what we multiplied by. Again, I will be posting a video or talking about in class why this works the way that it works, but this is simply an approach to, if I don't have an exact differential equation, can I find something to multiply it by an integrating factor so that I do have an exact differential equation? So I will leave you on an example to try. So give this one a shot. X dx plus x squared y, x dx plus the quantity, x squared y plus 4y times dy equals 0. See if it's exact. If it's not exact, see if there's an integrating factor you can multiply by to make it exact. If you can make it exact or it is already exact, then find the potential function guaranteed by the fact that it's exact, and then choose a level curve of that, and then choose your constant so that it meets these criteria. So give this a shot. I'll see you in the next video.